Okay. So there's five. They're going to do basically one thing, which is to go from discrete indices to continuous indices. Which will necessarily translate sums over integers to integrals, which would then necessitate changing what we mean by inner products and the completeness of the relation. Which will lead us to the idea of distributions, by which I mean we will introduce the idea of the Dirac delta function, which if you've done any quantum mechanics, for example, you would have seen before. And what I want to do is introduce the idea of the Dirac delta function, and then argue from the fact that it's not actually a function. It's a statistician would call it a distribution, a generalized function. And I'm going to introduce it not as a mathematician, but more kind of physicist way of thinking about it. So I'm going to give you some intuition for what it is, by what it does, and how we define it under the integral sign. And then we'll generalize that to, we'll do an example and we'll generalize it to high dimensions, and that will take us to the end of this section, I think. Okay, great. Okay. So let's focus on the set of square integral functions at some interval with respect to some weight. I want to consider the Hilbert space, the set of square integral functions on an interval from A to B with respect to the weight W. Okay. So to put some intuition, I'm going to stick with our notation of the basis. E X like this. Now, previously, I have considered the basis to be labeled by discrete numbers, K, and K with 1 to infinity. Now I'm going to assume that X is a real number. Okay. I'm going to define these objects by their relationship to the things that we know how to work with, which are functions. We'll see how it will all kind of make sense in a strictly analogous way. Okay. And because x is a real number, it will make more sense for us to replace EX with just x. This is the typical physicist notation that you would find. I don't know if you had a look at the book that I recommended, but in the Shankar, for example, this is the notation. Okay. So previously, where I would have E1, E2, E3, etc., you can just think of 1, 2, 3. Right now, we instead of going 1, 2, 3, we label by the real number x. Okay. So I'm also going to say that where I would previously have, the I components, so don't write it, just listen. Where I previously have the I components of a vector f as, and now I'm changing my notation, I in a product with the vector f, right? Was it good enough? Because it's super uncomfortable. Okay, so here's the thing, right? So previously we said fi and we wrote down ei. Now I just make an argument for instead of writing ei, I'll just write I, right? So ei would be e1, and e1 would be the vector that had component 1 there and 0 everywhere else. Right, I might as well just call this vector 1. It's a label, right? So this is how I would extract the ith component of the vector f by taking its inner product with the ith basis vector. Okay. Now, instead of saying s subscript I, there's nothing stopping me from having a function which I evaluate which has support only on the natural numbers. Make sense? So f1, f2, f3, f of 1, f of 2, f of 3, etc. Okay, so I've made this, push this label to functional dependence, and I've said that this guy only has support of natural numbers. Okay, so now it's kind of trivial to go from there to that. All right. So I have a vector f. It lives in the function space, and the function f of x is what I get when I take the inner product with the x basis vector and that function itself. This is my definition. Okay. This guy is going to be a square integral function with respect to the weight value on the integral function. Right? So now I can define the inner product on L squared HB as G product of F is the integral from A to B of G S conjugate F of X W of X dx. Those sums. Okay. Force. But then I use my definition of what this guy is. What all that on. And this is the integral from A to B of G X. And this is X in the product F. I'm going to define it by then. W of X dx. And I can take the integral inside. So get the integral from A to B. X W of X dx. x. Which must hold for any vectors f and g in the Hilbert space. And this is true if and only if the integral from a to b of x of the product of x w of x dx is the identity. And this is then the completeness relation for a continuous index. Remember the last time we had the completeness relation, we had a sum over all of the basis vectors. Well, what I'm doing is I'm assuming that the basis vectors are continuously indexed, and then I'm integrating out over that in the continuous index. Okay, so this is the completeness relation for a continuous index. That's going to be absolutely fundamental to everything that we're going to do going forward. Question.
I'm going to listen to previous lecture, but what's the significance of WX?
WX is just the general weight. So when I do the integral, depending on what that weight is, I have different types of integrals. So for example, you would be familiar with the normal Riemann integration, and then the Riemann integral is just W equals 1 for all of it, right? But this is a perfectly general statement that holds for whatever integral measure I choose to work. Okay. And typically, when you talk about defining inner products, you talk about defining inner products with respect to a particular weight, saying that your measure for your integral is not necessarily just a Riemann measure. Right? The Riemann measure is what you're familiar with, and most of the functions that we'll be working with you'll be using the Riemann measure as well, but it's not the only measure of the integral that I need to work, that I can. Okay, question? Why I take the integral out is because I'm integrating with respect to this x, and the x dependence is just here. So there's no x dependence, there's no explicit x dependence in either of these guys, so I can pull them on the integral. But I have to make sure that I keep track of the fact that this is a ket vector and this is a product. All right. So as long as I do that, I can put that in code. Yes. Sorry, I can't hear you.
I'm kind of not getting why, because like in the line above, and Q of X and F of X, isn't
F of x and Q of x are what I get when I project this vector onto x. So that's why I can't take this x out. There's no x dependence in f. The x, any of the x dependence comes from taking the standard product with the x vector. Yes.
Speaking of what is the dependence of f or is that purely vector?
F is purely a vector. Good. Okay, so that's the completeness relation that we're going to be using, and another way of writing this is okay. Let me say. Okay, so you remember when we had a basis of vectors, we were able to expand a given vector in that basis. So we wrote the vector f as f sub I ei, right? I can use this. This is called the completeness relation or the resolution of the identity. So I can use this to expand a general vector now in terms of the basis set. So vector F in the Hilbert space is the identity operator times F, but the identity operator can be resolved in the basis X like this. This is the integral from A to B, X, X, W of X, dx, operating on F. And I can take this F into the integral, and this F ket pairs with this guy. Right? Whenever I see a row vector, the ket vector will always pair to map to a real number or complex number. So it is the integral from A to B of F of X. That's because these two guys get together to give me F of X. And then what's left is this W of X, the vector X, all of that sitting inside the integral. So this then is a continuous version of the expansion of a particular vector in a particular basis. Everybody with me? Okay. So we can expand the vector F in the basis X, the continuous basis X like this. So let's take an inner product of F, that F, with some vector, let's say X prime. Okay. So X prime inner product F is the inner product of X prime with the integral from A to B of F of X. In fact, let's write it like this. The vector X function F of X, the weight W of X, all integrated with respect to X. Okay. This guy is broad. The only thing that it can act on is the corresponding ket. Right. So these two pair out together, and they give me, and I take it to the integral because the integral only involves X and not X prime, so it's a different variable altogether. So it's integral from A to B of F of S. X prime inner product X W of X yes. But by our definition, this thing here is going to be defined to be F of X prime. So again, F of X prime is the integral over the support of F of X times something integrated with respect to S. Right. So here I'm assuming that F of X has support only on the interval from A to B, and that X prime is in the same interval from A to B. Okay. That just makes things clear for me to work with. as a statement of how much I like you guys. This is my hardware on the top. There's 10 of them. And I'm using one of them anyway.
Also sweet.
Okay?
Also special.
Yeah. So I want you guys to show that W of x prime in the product x is equal to 0 if x is not equal to 0. Right. And it's equal to infinity when x is equal to x prime. I'll give you a visual picture of what this looks like if you haven't encountered it before. But and it's an even function of x minus x prime. And that if I integrate over a to b, w of x of x prime product x, then I get 1. So if it wasn't clear to you, already the statement of the exercise should tell you that this is nothing but the Dirac delta function. In fact, it's a generalization of the Dirac delta function with an arbitrary weight. Yes.
So, why does not really because you just choose X arbitrarily to be the real specific writing instead of just getting that from the division or if you
Which is the extra work you think we're doing?
when you try to understand when you
So the definition of by the definition of what f of x was. Right. So here's my definition of what f of x was, the projection of f of x. It implies here, that's what fixed out f of x from. But I have an expression for f in terms of this integral. My point is that here's my function f of x. Forgetting about vectors and stuff right now, right? So here's my function f of x. If I multiply that f of x with this something, which actually this is a nice segue to where I'm going. If I multiply this function f of x, right, by something, this whatever this guy is, I don't really care what it is right now, it's something, right? And I integrate out over the integral from a to b, then whatever this guy is, samples this function at x prime. Let me say that again. I've got a function f, right? If I take that function over its entire domain f of x, right, I multiply it by whatever this guy is. The only thing that I know about this guy is that it's a function of x and x prime, right? So I've got some function of x and x prime that I multiply this function f of x with, and then I integrate it out over its domain, right? And this guy has the effect of sampling this function at this point. Okay, and that's what this does for us, and that's why we need to do the extra work to show what this is. Okay, so that's exactly the argument I wanted to make. Tell you that this thing is called the Dirac delta function or the generalized Dirac delta function with delta of x minus x prime, which is defined to be the integral, sorry, which is defined to be this w of x, x prime integral that x. And it satisfies remember what label it was. And it satisfies property that if I integrate f of x over its domain support against this x minus x prime, then it's a sampling function that samples the function f at the other variable x prime of this expression. This is a very famous function that was discovered by the physicist Paul Dirac, the mathematical physicist Paul Dirac, in the study of quantum mechanics, which is roughly where we're discovering it as well. Okay? Quantum mechanics is basically the theory of operators on Hilbert space, according to the moment, but back in the day, you discovered that you had to have this relation because of this resolution of identity that gave you this property here. And then you had this weird function. I'll tell you why it's weird. Why you can see why it's weird already from here. This function is zero everywhere except at one point where it's infinity. But if you integrate this function over the domain, you get one. Yes? So it's not really a function, and then mathematicians took this, and this was the start of the development of the theory of distributions. So this was the first kind of distribution that we had to regulate, and it led to the general theory of distributions, following on from this. In the same way that when Newton exchanged limits and derivatives, it led to the theory of real analysis. Okay? And mathematicians look at this and go, why can I exchange these, the order of these things? Well, the mathematicians look at this function and find that it's something that's zero everywhere, except one point where it's infinite. And then you can integrate the whole thing, keep finding the area under this infinitely thin needle, turns out to be one. To make things precise, you introduce the idea of distribution. So technically, this is equal to it's equal to f of x prime is x prime is in the integral from a to b and zero otherwise. And I guess, yeah, that's all right, so let me do an example then. Give you some intuition. Give you some intuition for what this should be doing. So typically when you introduce the Dirac delta function to the undergraduate level, it's good to start with functions and define the Dirac delta function in the Dirac delta distribution as a limit of functions that you already know and work with, right? So I'm going to define, and for this we pick many different types of functions, whichever gives us the best intuition for. So let me give you some examples of what such a function can look like. And just for the illustration purposes, I'm going to assume that A is minus infinity and B is infinity. And so we're going to take the entire real line. So imagine I have a function that is 0 everywhere, except on the interval between 1 minus a half and a half. Alright, so it's 0 everywhere, except here, where it's 1. Okay? So this function is 0 everywhere, except on this interval from minus a half to a half, where it's 1. So if I calculate the area under this curve, then it's a half minus minus half, which is 1 times 1, which is 1. So the area under the curve is 1. And now I think of a limiting process. So imagine I halve this interval. I make sure that my function is, for the next function, I consider a function that is 0 everywhere except here, and then I double this like this. Right? So 2 times a half is 1. The area under this curve is still 1. Okay? I've squeezed the function a little bit. It's 0 everywhere, except in this little interval from minus a quarter to a quarter. Right? But I've got to double the height in order to make sure that the area on the curve is 1. And you can see that I can continue doing this. And in the limit, I can imagine that this function gets infinitely thin, so it's basically this blue line. And in order to maintain that the area under the function is 1, I have to send the function off to infinity, where the width becomes 0. In such a way that when I multiply the width by the height, I still get 1. As a limiting process. Make sense? Okay, so let me make this a little bit more precise. But I don't want to do it with this simple curve, because we're going to find that. So we're going to do it with a slightly more complicated curve. And for this curve, I'm going to use exponentials integrated between two points. So consider the function let's say t, which is a function in x minus x prime. And all that means that whenever I encounter x and x prime in this functional definition, they'll always occur in the form x minus x prime. Okay. And I'm going to define this function to be 1 over 2 pi times the integral from minus t to plus t of e to the I x minus x prime back to e dt. Well, it's an elementary integral, so we can do this integral. I'm going to leave it as an exercise for you to do the integral. So show this. This integral is basically just 1 over pi times sine of t times x minus x prime divided by x minus x prime. So if you want to get a feel for what this looks like, it's basically a sequence of functions that start off looking like this, and then the next goes they start oscillating, and then they oscillate further, So again, you can imagine that as you increase t, the oscillations become less and less pronounced, all amplitudes. And the central amplitude one is bigger and bigger, goes off to infinity. So the t goes off to infinity. So you're integrating from minus infinity to infinity. This goes to zero width and infinite height. So we calculate the area under this curve. I'm going to switch out the stroke because I can't see it on the board yet, on the camera, so I'm going to still with white chalk. So if we integrate from minus infinity to infinity of dt x minus epsilon dx, this is 1 over pi times the integral from minus infinity to infinity. So I'm calculating the area of these curves, right? As a function of t. Sine t x minus x prime over x minus x prime dx. And it's also an elementary result that the integral from minus infinity to infinity of sine x over x is pi. Then show that. So this is basically just pi over pi is 1. Okay, so there's some gaps in this example. I would like you guys to fill that out. But what this does for us then is it gives us a representation for the Dirac delta function as a limit as t goes to infinity of this 1 over pi sine t x minus x prime or x minus x prime, which is just 1 2 pi the integral from minus infinity to infinity. The definition that I had there, e to the I x minus x prime t dt. So again, here's something else that you might recognize. Anybody? Fourier transform. Fourier transform of the exponential. Okay, so the Fourier transform of the exponential function or the complex exponential function is nothing but the Dirac delta function. So this gives you another representation of what the Dirac delta function is as the Fourier transform of complex exponential. Okay. Very good. So everything that I've said applies to a continuous single variable function. But everything that I've said so far can easily be extended to multiple variables. So for example, instead of having a function f of x, I can have a function of a vector in real n-dimensional space, in which case I've got a function of f of x1, x2, x3, etc., all the way to xn. And I can define then vectors, I can define projection of vectors, I can define resolution of the identity, I can define the Dirac delta function with all of these things intact. So let me just say the following. Okay. Let me see the thought. All of this extends to multivariable functions. Let's say that's all x1, x2, all the way to x7. Which you can imagine find some vector this that dots into the vector f. Or if we define, say, the vector r, now I mean normal vector in a dimensional real space, which I'm going to define to be x1, x2, all the way to xn. It's an r vector, and let's say d and x, which I'm going to define to be dx1, dx2, all the way to dxn. How many of you did differential geometry in the first semester? For those of you who've done that, what I mean here is the wedge product between the one forms dx1 to dxn. Okay, this is implied anti-symmetry in here that applies to all integration forms. So then we'll define the vector get to be this one, two, and like that, with a multi-dimensional delta function, delta r times prime product delta of x1 minus x1 prime delta is 2 minus x2 prime delta minus x7 prime. So the immediate generalization then of what it is we're doing is the statement that the expansion of f can be written as the integral of f of r w of r where to get r integrated in dm x. This is now the multi-dimensional generalization of what we've already done in one dimension. The resolution of identity is the statement that and here the domain of integration I can write as, let's say, some generalized domain omega, which when I specify what the exact problem is, I can tell you what that omega is. It could be a rectangular volume, hypervolume, etc. So the resolution of identity is then the statement that the integral over omega of r w of r dn x the identity sampling relation is that f of r prime is basically just the integral over omega of f of r integral omega over f of r w of r r prime product r integrated over omega. And then finally, the definition of the delta, the Dirac delta, delta of R minus R prime is just R prime in the product R W of R yeah. Okay. I want to make one more observation about the Dirac delta, and then I'll stop. The Dirac delta also has the property that and you can prove this as rigorously as a limit, but it also has the property that its derivatives are defined also under the integral and defined by integration by parts as follows. The integral, let's say from minus infinity to infinity of f of x delta prime, meaning ds d delta by dx, x minus x prime dx is minus the integral of f prime of x delta x minus x prime. And now I have a conventional Dirac delta function acting under the integral. So where the delta function sampled f of x, this now samples f prime at x prime with that minus sign that comes from integration by parts. Okay. So again, where the delta function samples the function that we multiply it with at a particular point, the derivative of the delta function samples the derivative of that function with a minus sign. Okay. The minus sign now makes sense, right? Because the delta function is an even function of x minus x prime. So I would expect that its derivative should be an odd function of the x minus x prime, which is reflected in this minus sign. Okay. This here comes from integration by parts. So the minus sign. That minus sign is precisely what makes the derivative of the delta function an odd function. And then if you go back to what we learned about functions first year, you have an even function and take a derivative of that even function, then it's an odd function. Okay. And in fact, we can use this idea, generally speaking, to define the derivative of bad functions that don't have derivatives well defined, by integrating by parts against a good function whose derivative is defined. I'm not going to go into that in much more detail. Next time we will talk about Next time we will talk about the support of functions. In particular, I want to talk about functions that have compact support. And the reason why we're going to do this is because we're going to move on to operators for the next session and next section. And a really super important class of operators are operators that have compact support in the office space. So these are compact operators. Okay. Good. I will email out shortly the first exercise.